I would like to introduce Srabanti Chowdhury. She is a professor of by the way, this person here makes me realize how little I've accomplished in my life. She's a professor of electrical and computer engineering at the University of California, Davis. And as a professor and technology enthusiast, she enjoys doing research and teaching students about new technologies and how they impact our world. As a mom of a 5-year-old, she's getting good at juggling, well, metaphorically speaking. Can you actually juggle?
Kind of, I'll try between Gallium.
So I'd like to have Srabanti tell us about her work.
Thank you for that very nice introduction, and this is very exciting actually. I should have asked all my students to join, but probably they're so bored of me. I won't try that trick on them this time. So let's continue from where Ron has left, and I believe even though we didn't quite discuss too much about our slides, but you know, the way he actually sort of put together his gallium slides made my job very easy. So you will have to go through the boring part right now. How do we make gallium nitride? Something that Ron already shared with us. So I'll go straight into, again, like I said, there will be some overlap and repetition, but that's good. That will make you remember this forever. So, so gallium, like Ron has been talking about, is the metal, the magic metal that makes that you can actually melt in your hand and makes the spoon disappear. Just don't drink the tea. That was basically Ron's plan. We didn't go that far. So, but it is quite non-toxic, so that's good news. Melting point. So this is a recap. So it's kind of melts at less than 90 degrees Fahrenheit or less than 30 degrees Celsius. And the sad news, it doesn't really exist in the elemental form in the earth, so you don't find gallium just like you can find silicon to a great degree, like go to near a beach and you find silicon in silicates. Here, in a similar way, it kind of exists with other in compounds form like bauxite or spherulite that Ron was talking about. So you can actually get gallium as a byproduct. That doesn't make it that cheap, but nonetheless, it's a byproduct. So there's a way to get gallium. Just kind of showing you how we call it is it's a group 3, okay, group 3 element. And this guy's aluminum, indium, which fall in the same column, actually plays a very important role in what you just what we showed in semiconductors, actually, okay? So I'll come to that in a little bit. So let's do a little bit of what gallium has produced so far. So gallium in semiconductors. So I think most of us are familiar about semiconductors because almost everything that we touch and feel today are either made of some form of semiconductor chip. Mostly we known as silicon, but there are other forms of semiconductors, and some of them, as it is shown here, do contain gallium, okay? So gallium and arsenic makes gallium arsenide, gallium and phosphorus makes gallium phosphide, and then gallium and nitrogen gives you gallium nitride. So these are called group 5 elements, and these are group 3, as I pointed out. And you can see how the group 3 and group 5, that's a very nice ratio actually. 5 plus 3 is 8, which is actually what makes a shell of an atom complete. That means 5 plus 3, 8 is a closed shell structure, okay, closed shell configuration. So that kind of says that these are stable compounds, okay. But and of course, gallium arsenide has, at one point of time, people thought gallium arsenide will replace everything that we see in silicon or make with silicon. That didn't happen, which is not so good for gallium arsenide enthusiasts, but silicon people like it that way. But it exists, as Ron was saying briefly, that they do exist in your cell phone. So they use what is called a power amplifier. In every handset you have a power amplifier. The base stations use amplifiers. Those are made of gallium arsenide. The problem is arsenic is not such a friendly element. So we are a little scared of arsenic. So we thought that we might move all those applications to now with gallium nitride. So things that were made of gallium arsenide can be made, not everything, but a lot of these power amplifiers are now made with gallium nitride. And nitrogen is much more friendly and benign, so it's a good news. So some of the applications, like I will be mostly pointing to applications, are near-infrared lasers, solar cells, some very expensive solar cells that are used in space missions are made of gallium arsenide, high-speed radar, very high frequency. Anything above 250 gigahertz need gallium arsenide because electrons really zaps through the crystals. It's really fast, okay? Very close to the speed of light, which in electronics means one of the fastest you can get. And then, as I was saying, cell phones in the base station and handsets. Okay, so now let me talk a little more about the gallium nitride. This is something I work with. We make gallium nitride. I'll show you some of the wafers that comes out of our lab. And just in here, it's basically the opposite kind of the spectrum I'm showing. So now we are showing the three group 3s, aluminum, gallium, and indium. They're actually called the 3 nitride family because they together make many cool things happen. So aluminum bonds with nitrogen, very strong bond, by the way. Aluminum nitride, gallium nitride, and indium nitride. And that has quite changed the world. So the good news again, they're non-toxic. And even though gallium doesn't exist in us, as Ron was alluding to back during his talk, but these are biocompatible. So today, actually, you can actually make a teeny tiny gallium nitride chip and you can have biocompatible applications. Things are happening like in colonoscopy and things like that. You are actually making a small tiny chip of gallium and you can digest it. It's really not going to kill you. I mean, it probably will help you in the long run. But so basically, this is very important for us. It's biocompatible. So a lot of the biocompatible applications and medical applications are looking into this material, okay? Okay, so let me talk a little bit about the gallium nitride and the LED. So I actually studied at UC Santa Barbara where LED was invented. Shuji Nakamura, whose picture was shared in the previous part of this talk, happens to be one of my professors, and actually I thank him for sharing some of his slides here. So I'm going to show some of his slides, and I cannot say enough about the LED, but as we all know, it has quite changed and transformed the world we see today. So light, lumens per watt. 1 lumen is basically the amount of light that a source emits is expressed in lumens, okay? And as you can see how the trajectory went from an oil lamp to an incandescent bulb to a fluorescent lamp, and now we are in this LED era with over 300 lumens per watt, okay? This is a very, very steep rise. A 60-watt incandescent bulb produces almost 860 lumens, okay? Which, if you make it with an LED today, will consume less than 5 watts. So that kind of tells you how efficient lighting is because of LED. Now, how did that happen? So again, this is a little bit of a recap. The white LED was possible because of gallium nitride. So this is a white LED, a packaged LED, and this is the bulb. Ron has displayed it. Thanks, Ron, for that helps us. So again, LED today is the basis of more than 15 billion and growing, as you can understand that population increases, and places where you cannot get the grid lines or the electricity cannot be transferred to grid, you can still get hold of a battery and you can light up an LED, right? So this has a huge significance in today's world. Okay, now a very quick cartoon of what and how an LED works. I have to share this. I mean, this is something my undergrad students would not appreciate very much probably anymore. But basically, what this shows is it's a battery. You bias or you put voltage across this material, and this is what the red part is, what is called the active part of the LED, okay? You have, let's call this a substrate, which is basically the foundation. By the way, gallium nitride is grown on a substrate, okay? So this is the foundation of the whole chip. Then you grow the source of electrons, or also called an N-type material or N-type layer. You sandwich the active region, okay, the active or the light emitting layer, and then you have a P-type region, okay? So both P and N can be made out of gallium nitride, and this active region actually is made up of gallium nitride, but you put a little bit of indium in it, and that's the trick, okay? I'll show you how. So basically, that emits the light. What happens is this electrons and holes, the electrons are sourced by the N layer, the holes are sourced by the P layer, they're combined, they recombine, we call it, and they give out the light, okay? And going to a more fab-like picture, so this is an actual chip, okay? I have some of the chips, I'll demonstrate here, and this is the packaged blue light, okay? So this is from the chip to a package, and how you get the different colors is even more interesting. So what you do is you change the, remember what I said here in the active region, you have indium, okay? So you change the composition of indium into the gallium nitride, and by that you can change the color. So you can add more indium and it becomes red. Well, we're not yet here. A lot of research is going in this region, by the way. If you just have a pure gallium nitride, you get sort of violet, okay, close to UV kind of light. Then you add a little more indium, you get more sort of a cyan green. Then you get a true green. Then you go to yellow. You keep adding indium more and more to gallium nitride, and you get towards red, okay? And believe it or not, a lot of work is happening here. It's one of the hotbed of research right now. How do we make a red LED all from gallium nitride, okay? Why? Because ideally we want to have RGB, the three primary colors. If you have three primary colors, you can mix them in any proportions and you can get any kind of light out of it, right? So that is why we want, so that we can integrate everything, we want in one chip, we want all R, G, and B all in gallium nitride, okay? Where are we today? We are here. We have nicely achieved this actually. So we have blue light and yellow light, and we can mix them to produce white light. And this is exactly how white light was produced. That bulb you see, that has blue and yellow to make it white. Okay, so this is basically what it does. You have a blue LED which gives you a blue light. You convert the blue into yellow using phosphorus, and you then mix the two to form white. This can be done with other colors also, okay? And this is how the white LED was produced. So I'm going to show you something that we get from the lab, and this is only one chip of LED, okay? And I'm just taking a battery. Let me make sure. So I have a positive and a negative, and I don't want to. So, ooh. That's bright. So this is one chip, okay? A company very generously packaged it for us, and I was lucky that this happened right before this talk was scheduled, so I was able to just get it from my lab. So there you see, it's one LED, not how you, oh, it blinds me almost. And so this is pure blue, correct? Now we add the phosphor. When we add the phosphor, this is a warm white. So this is one big LED. Now you guys can see, right? So that is what you see in those bulbs. So these are, I hope, some cool examples how, and then you can of course make cool white. This is also done using several of those chips, okay? And this is more, you can see the cool and the warm just indicates the color temperature. This is a cool white, that was the warmish white. But this is as close to a wafer stage you can see, basically, of gallium nitride, as close to the fundament or basics of a wafer. Okay, let me see. Okay, so moving forward, let me. Oh gosh, so I hope that is exactly how we are getting white LED, and I hope this kind of shed some light how we see today's all the white bulbs that you can buy in a Home Depot. So, of course, very well deserved. The three people, or the three guys who were responsible for inventing the blue LED and were awarded the Nobel Prize in 2014. And this is very important. One of the reasons I kind of highlighted this, that for invention of efficient blue light emitting diodes, which has enabled bright and energy saving white light sources. So it wasn't because they invented LED, because LED was invented way before the gallium nitride LED was invented, but it's because this enabled white light, and once you have white light, it completely changes the world. Perhaps only credited by a Nobel Prize. So this is how the trajectory goes. The rise of this LED market, as you can see by GAN, has basically has a very, very sharp and steep rise. And I mentioned, I repeat, it is basis of a $15 billion plus market and growing. So moving forward, there are other emerging applications that these are coming. These are all part of the research, some of it which we do in universities, some of it is done in the industry. But other than decorative lighting, automobile lighting, displays, there are agriculture. People have shown that some of the herbs and plants grow much better under certain wavelength of light, indoor lighting. And then there is another thing which is very coming to practice a lot, is basically LED visible light communication, or VLC. So the next generation of lighting actually starts with a blue laser, and some of the automobile headlight is right now with a blue laser that has already started. Okay, so final part of my talk, this is something that I work in my lab. This is about power conversion. I won't go too much into the details, but let me explain the way these things work. You take energy from one state and you convert into another state, and you do it by basically chopping the energy and then using what are called switches, and then reassembling them into the desired form at the output. Okay, that's what is called a power conversion. So you can take a DC, convert into an AC, or you can take 150 volts, convert it into a 12 volts. Okay, so these are called power conversion, and what makes power conversion possible are these tiny little things called switches. Okay, so I make switches in my lab. My students make switches in lab. And how do we make them? We make it again with the magic material called gallium nitride, which is one of the most promising material that can change the way we see power conversion today. So just so that you know, the amount of energy we lose in inefficient electronic switches is more than what we produce by hydro and wind and solar together. So this is the loss, and this loss is more than what we generate by renewables. So that is because we are using silicon electronics. Silicon electronics has brought us here, which is great, but we have a lot more to do. And one of the things that we do, what we are trying to do is make things more efficient, just like in the lighting it happened. We are trying to do that in power conversion, so we use gallium nitride for switches. This is a fantastic test bed for showing gallium nitrides are basically showing how power conversion works. There are many components, but one component you can understand easily is onboard chargers. So there's many other, especially in the world of or in the generation of autonomous driving. There are much more applications that hasn't happened with silicon and will never happen with silicon. There, gallium nitride can play a very big role. Wireless charging is one of them. Okay, I'll go to this this slide, which has a lot of data, but all I would ask you to kind of pay attention is the reason why gallium nitride is helping in this host of application is by running things at higher frequency, because when you can make things go fast, you reduce size, okay? When you reduce size, you make things portable, you make things compact, and I think everyone in this room will appreciate what it means to reduce form factor, what it is to reduce size. So that is one motivation to do gallium nitride. The other motivation is you can make things run hotter. So all this electronics, when you convert power from one state to another state, produces the waste. You know what the waste is? That is the heat. So if you touch the charger of your laptop after 2 hours of working, you will feel the heat, and that's the wasted energy. What we are trying to do is we are trying to reduce that waste by going to a more efficient semiconductors, okay? So there are certain things that are happening today, like photovoltaic inverter. This is the size by silicon. It becomes less than half. It reduces cost ultimately. And very important, saves energy. As I said, that power conversion actually wastes energy more than produced by renewables. That's a very alarming factor. Moving to the very, very last segment of my talk, the lab. So I want to show you a few things. This is how we grow gallium nitride. The chemical reaction is we take ammonia, we split it, that are called cracking. Ammonia cracks around 600 degrees C, and we use gallium as a trimethyl gallium, TMA. So basically it's a metal organic compound. We crack ammonia, we take the nitrogen, and then we form gallium nitride, and the other product is methane. This is how the reactor looks. So this is actually from my lab. This is where we are making gallium nitride, and this is the product. So it's kind of the, how it looks when it comes out of the reactor. These are called MOCVD, metal organic chemical vapor deposition reactor, and we grow GaN. Unlike many other semiconductors where you can actually extract out those compounds, gallium nitride needs to be synthesized chemically, and that is why we call it we grow gallium nitride. And this from GaN wafer to transistors and IC, a lot of steps happen between here and there. And one important thing I want to bring up, the reason gallium nitride became so popular in power conversion is because we were able to grow it on silicon. Silicon is dirt cheap, and that is extremely important because with every technology we want to reduce size and make it cheaper. So how we will get there? The only way we can do it is if we take help of silicon. So we have started growing gallium nitride on silicon, which can be very big wafers. So silicon can be 10-inch wafers, right, in diameter. So this is a gallium nitride on silicon. There are other substrates. You can grow gallium nitride on sapphire. I have an example here where we basically grow gallium nitride on sapphire. Okay, and this is basically how it looks when it comes out of the reactor. And this is not just gallium nitride. It is grown on a foreign material, as we call it, or a substrate called, remember that foundation, if you remember, like in one of my slides I called it a foundation. That foundation is very critical, and that is called the substrate. This is how a transistor look. My students work very hard to make them. I'm very glad at that. And then we can make ICs. Basically we can make circuits, so on and so forth. The very important factor, smaller form factor, higher operating temperature, lower in cost, lower in energy. What else do you want? So basically, so that concludes my I don't want that music, but that's okay. So this is the vision of tomorrow, okay? This is how crazy things will look like. So now, nothing is hitting, even though cops are happy because they don't have to do they don't need a job actually at that point probably. I shouldn't say that. Well, whatever. So this is how crazy the world is going to get, and yet we will all live, right? So what do we need? We need very smart technology which cannot happen without gallium nitride. So all this LiDARs, radar, power converters, sensors, detectors, wireless charging, they all, and this is so true actually, they're all probably 80% of them will still be silicon, but 20% is a lot of all that, okay? And for that, 100% you need gallium. So with that, I would just thank all my group. This is my research group, and I would definitely acknowledge for people who helped me gather some of the slides. And I would, of course, a lot of this research was possible by the government-sponsored government agencies who fund this kind of research. So I'll conclude at that, and thank you. I'm happy to take any questions.